my background is 40-some years in lens design. That's what I started out doing way back in the 70s. And so I was at Lockheed 36 years. I was their optical designer there, and then I started my own little LLC afterwards, and had a lot of interesting jobs like Caltech. I'm working for Caltech right now on some telescopes. But there's a 15-inch refractor out there, great big job. I haven't seen it yet. I want to get up there at Comanche, and made by B&G. And this is, I had to throw this in. You want to light? This is my buddy Jim Egger up in Anchorage. We were talking to each other on cloudy nights, and he had the glass for that big 9-inch and 9-inch lens. And this guy's a refractor freak. He's got the biggest refractor in Alaska. This is it. And Alaska is at 64 degrees, so if you look at that polar axis, it's like this. The North Star is like that. But that we went up to see him in 2014, and so this is the one at Three Rivers is going to be bigger than this. So yeah, I helped him. I designed the lens for this one for him. He made the curves. Refractors. Okay, we've got reflectors and refractors. Reflectors don't have color error. The light reflects off a mirror, whether it's infrared, ultraviolet, visible, everything in between, they always reflect. But lenses act like prisms because they're dispersive. They have a different refractive power for different wavelengths. So what happens is if I've got a positive lens and I've got a white light ray coming here, then the lens will bend like a prism. If you think of this as a prism shape, it will bend blue more than red. Now if I flip the prism upside down, I've got a negative lens here, and it bends toward the axis of being red more than blue. So it kind of makes sense that if you combine those together, you can get all the colors to come together. Well, it doesn't quite work like that because of the way glass works. But you can get in an achromat, like the one at Three Rivers, you can get two colors to come to the same focus. But in this case, it's designed for red and blue, which is your hydrogen alpha and hydrogen beta, as Sam talked about. H beta is 486 and hydrogen alpha is 656. You get those two to come together at one focus point, but then because of the way the glass bends light at different wavelengths, it's going to be out of focus at green. And what this disparity is called the secondary spectrum, and that's what all two-element achromats have. How many of y'all have apochromats where they've got 3 elements in there? They have, yeah, like Sam's got. They bring a whole bunch more colors together. They can bring 3 or even 4 colors all together at the same focus. So this is what's called secondary spectrum, and this is what the Three Rivers refractor has. And I just have a little history here. I'll plane through that. It was invented in 1729. You can imagine that. And Fraunhofer made the best one. It's 2-element. And now the Fraunhofer design is what's used in all the big telescopes. Yerkes Lake, U.S. Naval Observatory, Piccolomini, all the big ones. They're 1 meter to 24-inch size pieces of glass, so they're heavy, and they can bring 2 colors together to a common focus. And typically, this is your human eye response here. Your eye peaks at green light, which is 0.55. Your eye is most sensitive to green light, and it's not so sensitive at red and blue. So what you do is you bring red and blue together to a common focus, and then the green light is out a little bit. And this is the picture that Keith took, and you can see the effect of that is you've got a sharp center, a yellow-green center, but you've got this out of focus blue and red light surrounding it. And he took this with this is Alpha Hercules, that's right. Correct. And so I thought this kind of demonstrated well that the little cheapo refractors you get from Kmart and Target to the high-end ones from B&G, iStar, all those places, big refractors, big lenses, if they're not what's called apochromat, then an apochromat can bring 3 or 4 or 5 wavelengths to the same focus. A refractor and most people who are forward like me, will bring 2 colors to focus, and the rest of them are out of focus. So what's the image look like? You kind of got to focus for what looks best for your eye. What that means is if you look at Venus through a refractor, you're very likely to see a big purple-blue haze around it, and you'll also see a red haze. It'll be sharp. Venus will be sharp in the middle. How many people know what a Bader blocker filter is? You put it over your refractor, over your eyepiece, and it blocks the purple and blue light from coming to your eye, and that makes the image sharper because it gets rid of all this. Imagine if you had a filter, like Sam was talking about, a color filter, that only allowed the light from the center tight core. That refractor would be super sharp. And I've got one of those, and it tints the image a little yellow-green, but it really does sharpen up the refractor I've got. But this is the problem, and this is what's going to be present in that 15-inch refractor. So what I did was, I hope this shows up well, these are pictures I took from the backyard. This is the Orion 130 millimeter, 1 meter long refractor that I've got. And then a few years ago, I coughed up enough to buy a Takahashi, which is a true apochromat. And here's the difference. Look at these stars. You see that blue halo on all of those? The brighter ones, it's not there. This is a 3-element lens that brings 3 colors to a common focus. But when you bring 3 colors to focus, all the secondary spectrum squishes down as well. So it's almost a perfect image, almost what a mirror would give. And so these are just short shots from my backyard, but it really showed the difference. I rotated the orientation, but I got them the same. Like that star there, it's nice and light and tight, and over here it's soft. Notice also that these exposures are about the same. Because you're focusing more light into the same point, the stars are brighter, and that you can go deeper, and you get fainter exposures than you do with a refractor. So it's well known the refractor is not a very good deep sky photography instrument, but the amount of color it has still makes it, limits it. Now this is a Hubble picture before they corrected the optics. No, it's not. I took this. This is through that same thing. This is the Hubble, the M42, the Orion Nebula, through that refractor I had back in my, it was like 2006 or 5 or something. Again, with the great big blue purple halos around the stars, and then when I rephotographed it with the Apo, notice the stars are tighter. The seeing is probably equal, probably like it is tonight when we should be out looking instead of sitting in here. But pretty sharp imagery here, but that's just all a refractor traditional achromat can do. And you get a 3-color lens like this one, then yeah, you can see fainter stars, and the ones that are there are sharper. So that's the difference. And now, so I get back to why cameras have the sensor in a camera that you photograph with sees and images a lot wider spectrum than your eye does. Your eye is this little seemingly narrow Gaussian here, sort of called a photopic curve. Again, there it is. It's peaking at about 5.5, and it's only about 10% responsive out here at H beta, which is 486 and 656 H alpha. So, and it's nothing. The eye is totally blind out here. If you've ever seen the color out here, this is deep, deep red, almost brown looking. If you ever go into the kitchen at night, turn on an electric range, just a bare second that you can actually see the coil starting to get put off light, that's out in this area. You're starting to see a little bit of infrared with your eye. But by the time it heats up enough to cook, boil water, it's up in here. It's red and orange now, hot. And we'll look at what the CCD camera can see. This is a CAT 8300 sensor, kind of typical of an astrophotography sensor. My gosh, you're talking hundreds of times more sensitivity out here than the violet and indigo. In fact, 350 nanometers, that's ultraviolet. And then way out here in the near infrared. So these sensors see a lot wider spectrum than your eye can. What I just said is that a refractor with all that color focus area it has, it still looks pretty good to your eye because you're not seeing all that out of focus energy. but a camera will. And again, I just zoomed in on a little part of it here. This is in the M57 Ring Nebula picture. This is when the Acromat, you see all that blue halo. And this is really zoomed in big. This is what you get with a really expensive scope like that Takahashi I paid $5,500 for. But it's a nice lens. So we just don't see as wide a spectrum with their eyes. They're great, they're fantastic, they're still the best camera in the known universe. They're amazing, but they don't have the width of the spectral coverage, okay? So when you take a picture with a refractor, you get what's called blue bloat. You can see how this is all bloated up, and if there was a double star hiding in there, you probably couldn't see it. And so you need what's called a monochromatic lens, which brings 3 or more colors to focus. And being a lens designer by trade and then lens design by hobby, I said, think about that one up there at 3 rivers and see if I can clean it up. So I found out it's pretty easy to correct the 3 rivers to take the 3 rivers refractor from this kind of imagery to this by some corrective lenses. So this is my guess. I called and talked to the D&G, and they couldn't give me the curves for the one out there. They couldn't find the record, or they couldn't, they didn't want to tell me. That's okay. But, so this is my guess at what the D&G Acromat is up there at 3 rivers. It's 15-inch f12, 180-inch focal length.